Good morning. I am Abhijit Gurnoker, lecturer at Information Technology Department, Vileparle Kelvani Mandals, Sri Bhagubai Mahatal Polytechnic, Mumbai. In our course, Fiber Optics Communication, today we are going to experiment on coupling losses. We are going to measure coupling losses in optical fiber using alignment model. Experiment number 4. The aim of this experiment is measurement of coupling losses in optical fiber end gaps using alignment model. The lab outcome: the students will be able to deduce how to couple how coupling losses are affected by in-gap displacement, lateral displacement, and angular displacement or mismatch while coupling light from one optical fiber cable to another between the joints. Also, students will be able to plot graph relationship between displacement and coupling losses. Experiment setup: equipment required: 950 nanometer infrared light source, LED source, detector, transmitter kit and receiver kit, 2 meter fiber, or you can say 1 meter 2 unit optical fiber cable, well power supply, well test CRO, function generator and alignment model. Equipments required are function generator, well power supply and so on, that I just listed before, right? So that we can able to give input using function generator and output can be seen on CR. This is the picture and schematic of alignment model. This alignment model is middle part is square model and this part is angular model and has two screws where we can fit the optical fiber, right? This model also has lateral scale as well as end gap adjustment scale from 0 to 4 millimeter. So it is, in this case we have 10 millimeter. By using this screw, end gap displacement screw, we can adjust in the gap between two fiber ends by 0.25 mm. Similarly, by using this screw, which is lateral adjustment screw, we can rotate it either clockwise or anti-clockwise to make motion of this model laterally, either left upper side or lower side. The third part of this model is this angular scale or angular model, which can rotate, right? We can increase or decrease the angle over the scale. The model has notches are provided like this when you measure angular displacement. Middle notch, which is coinciding with the centroid axis of the fiber to another fiber end, right? So this model we are going to use for our measurements, called as alignment model. Lab experiment setup: we have connected power supply, two power supply we use, one plus minus 9 volt and one plus 9 volt power supply connected to transmitter. Then function generator is connected to transmitter input, where we have fixed the frequency at 1 kHz, 2 volts peak to peak, and receiver's output is connected to CRO, so the output is visible on the CRO. Then we connected 1 meter fiber from transmitter to the model into this part, and it is fixed using the screw. and second 1 meter fiber is connected from model again back to the receiver, and receiver's output is connected to CRO. So in this experimental setup you can see equipments, power supplies, CRO, function generator, transmitter kit, model alignment model, and receiver kit. So we are use analog transmitter, alignment module, and analog receiver. The theory behind this, we will have end gap displacement. The gap between two ends can be measured in millimeters. Then we can have a lateral movement between two ends, and that lateral displacement can be calculated in millimeters. And also we can create using alignment model an angular displacement, the angle, and we are going to see the relationship between these three displacements and the output at the another end of the fiber. Good morning. Today we will study investigation the coupling losses when we connect two ends of the fiber. First type of loss is lateral displacement. Second type of loss is end gap displacement, and third type of loss is angle between two ends of the fiber. For that purpose, we will use this optical fiber alignment model, where we have a model which can move laterally in this fashion. Then we have a screw adjustment here by which we can move this model back and forth so that end gap displacement can be increased, and we have this third model by which we can increase or decrease the angle. Now what we will do first, I'll explain you how the connection has to be made first, and then we'll see how to proceed and how to measure the different types of losses. So first of all, I will explain you the connection. We have connected function generator. We have set the function generator at its frequency is 1 kilohertz, and output voltage is 2 volts peak to peak. So we have connected function generator here with about 1000 hertz frequency and 2 volt peak to peak as an input to our analog signal, analog transmitter. Then analog transmitter output, this input is also shown on the CRO. So first channel of my CRO, dual trace CRO, is showing the input which we have given from this function generator. Then we have connected this kit, analog transmitter kit, to plus 9 volt battery, and we have connected receiver kit to plus minus 9 volt battery. Then we have connected fiber, 1 meter fiber from this light source, light emitting diode, and it is connected into this photo detector, and this output of this receiver kit is connected into channel 2. So you will be able to see after traveling 1 meter distance, my output is being shown on the screen. First waveform is a triangular waveform, which is I have directly connected through this function generator here, and second which is the output of analog receiver, is connected to CRO into second channel. Now objective here is that we now know how much is the optical power is coming to this tip of fiber, that is after 1 meter fiber. So we have connected 1 meter fiber in this, and we have just calculated at the moment my output is 1 division, 2 division, 3 division, 3 into 0.1. So my output at the moment is 3 divisions multiplied by 0.1 volt, that is about 0.3 volt. After traveling 1 meter fiber, my output is 0.3 volts. So what now I am going to do is I am coupling this power, optical power, into the model, and I will press down this screw so that I have set this model at its default values. So center of this, there are two models, one is this and the second. Center of this both are being aligned by means of a central line. If you are able to observe here, a notch is given. That notch is maintained. So lateral displacement, we are going to connect one fiber here and second fiber from this end to the another end. So I am going to connect the second fiber. Currently, this module with the default displacement between these two modules is of about 3 millimeter. So the distance between these two fibers is already 3 millimeter, and so that my output is decreased because I have now connected 2 meter fiber, and now my output is almost gap displacement is there. And if I go like this away from my hand, both the hands, if I am moving, then lateral displacement will be there. And angular displacement will be if I consider the another hand, this hand like this and this hand straight away. So you have an angular displacement. So same concept we are going to do is here. We are going to connect one fiber here and second fiber from this end to the another end. So I am going to connect the second fiber. Currently, this module with the default displacement between these two modules is of about 3 millimeter. So the distance between these two fibers is already 3 millimeter, and so that my output is decreased because I have now connected 2 meter fiber, and now my output is almost, let me adjust it, my output is 1 division, 2 division and 3 division at about 50 millivolts. So 3 divisions multiplied by 50 millivolts, it's almost 1.5 volts peak to peak. So it's almost half what we have measured here, and after 1 meter fiber, again another 1 meter fiber, I have connected 2 meter fiber. First when I have measured it was 1 meter fiber, now I have connected another 1 meter fiber, and now my output is about 0.15 volts. Now what I will do,